Alright, so I think we can start now. So what we're going to do is I'm going to be recording some of our discussions so that you will not be falling behind of our discussions. I'll be recording this in advance. Okay, so if you have questions, I'll be also be adding some recordings of how I'm going to be solving some of the problems here. All right, so we're going to be adding more examples so that for your references on how to answer such questions. All right, so for now, we're going to be dividing the discussion into three parts. Okay, mainly in terms of counting, permutation, and combination. So the first part is with regards to counting. Okay, so before we learn on probabilities and uncertainties and other principles like that, and also outcomes, we need to know some basic counting theories, right? When we say counting theories, these refer to, okay, what is it? Okay, counting actually refers to the possibilities that are coming from experiments and processes that leads to outcome. Okay, counting theory also pertains to the set of all outcomes in an experiment, or the set of all outcomes in an experiment is called a sample space. So let's say, for example, you have a you toss a coin. Okay, the sample space there, or all the possible outcomes that can come out of that result, okay, whether a heads or a tails, is what we call a sample space. So the result of heads and tails is collectively what we call a sample space. The goal is to count all the possible outcomes in an experiment. So that's what we are trying to do. What are the possible or the possibilities of such actions of doing so? Let's say, for example, you toss a coin again. Okay, that will be our best example. Okay, all of the possible outcomes of a toss coin is a heads or a tails. Okay, so I hope you're getting the gist of it. Later on, we will be diving further into this theory. Okay, counting theory also refers to the set of techniques used for identifying the total number of possibilities of a statistical experiment without enumerating the elements of the sample space. So this refers to all of the possibilities. Okay, specifically, this becomes important in statistics mainly because all of the possibilities are collected. Okay, all of the possible results are possibly collected, and then this is where we measure probability. Okay, so let's say, let's go for some examples of um, what are some of the things that we need to know on counting theory. Okay, wait a second. Okay, first one is the multiplication rule. When we say multiplication rule, okay, this is the first rule that we need to know. Multiplication rule refers to the multiplying of all of the possible outcomes with regards to another set of possible outcomes. Okay, so let's do an example. Let's say, for example, you are flipping a coin at one time for 2 rounds. So you have 2 rounds of flipping a coin once each round. Okay, so for the first round, you have the possibility of a heads and a tail. Alright? So, well, it's just the same naman, no? Wala no problem doon. We all know that in the first round, you have a heads and a tail. However, in the second round, if you got a heads, alright, therefore, in the next round, you also get possible of a heads and a tails again. Alright? If you're gonna look at the example, only the possible outcomes that you can have in the second round is also a heads and a tails. However, with reference to the first round, right? If you got a head, all right, in the next round, you can also get a heads and a tail. Therefore, the combination that you can have, or the possible combination, okay, of the first and the second round that you have is what? Is 4. Why? Because in the first round, you may get a heads and a tail. That's one. Okay. And then two for heads. One for heads and then one for tails. So those are two. Now, if you get a heads in the first round, you may also get a heads or a tail on the second round. Okay. So that is what? Already two. And then if you get another tails, okay, on the second round, on the first round, you may get another heads or a tails on the second round. Okay. Now, if we're gonna be looking at it, no, we actually got how many possible outcomes. We got heads, tails, head, and then tails, tails. Okay, so how many possible outcomes are there in this kind of experiment? There are, right? There are four, correct? So, you get it? Hope you can get this one, huh? Okay, so there are four possible outcomes because the result of the first round, okay, is also with reference to the second round and vice versa. Okay, now let's say you have a third round. Of course, it will also branch out to the possible outcomes that you have before, okay, a heads and a tails. However, if we're going to record the possible combinations of the first, second, and third round, then this is what we're gonna be getting. Okay, we're gonna be getting what? How many? How many possible outcomes? There are one, two, three, four, five, six, seven, 8. Right? So as you raise the number of rounds, no, the number of possible outcomes also increases. Okay? And it increases in what way? Okay? Suppose that you have um, what happens if you got 4 rounds naman? So, how many possible outcomes are there if you flip a coin? Okay? At in 4 rounds naman, for 4 rounds. So, 4 times naman ka naman magka-flip ng coin. So, what are the possible outcomes with reference for each round can you get? Okay? So, later we will be solving this. I'm gonna have another video that will be solving more of like this. Alright? So, for now, just take note of it, and then we will be doing some calculations later on. Okay. Next is that here is the multiplication rule. So if a task can be performed in n ways, so if for each of these a second task can be performed in another n ways, n2 ways. Okay. So n1 ways and then n2 ways, and for each of the first two, a third task can be performed in n3 ways or another number of ways. No? So on and so forth. Then the sequence of k tasks can be performed as the first task, the number of the first task, or the number of ways the first task can be done, times the number of the second task can be done, times the number of the third task that can be done, and so on until you exhaust all of the possible number of items that you're going to be considering. So for this example again, for the toss coin, okay, how many tasks or how many possible number of ways can a coin have an outcome? Or how many outcomes does a coin have? So we have 2. So our N1 has 2, right? Correct? In the second round, our N2 is equals to 2 as well. Correct? So N1 here is 2. And then for the second round, also 2. Because you only have the coin, no? So in the third round as well is you have 2 as well. Again. Okay? So that will be 2 times 2 times 2. That will be 8. And then, try to check. If you have 4 rounds, and then you do the multiplication rule, how many rounds or how many possible outcomes are there if you have 4 rounds? Alright? So, we're gonna be computing that later. Okay, take note of this formula. This will be very important later on. Okay? So, we will be using this as we go. Okay? So, take note of this one. Can I flag this? I cannot flag this. Let's just put a highlighter here. Okay, take note of this formula. It doesn't highlight. Okay, there. Take note of this formula, okay? So don't forget about that. Okay. And then we will be doing more exercises later on as a sample. Okay? So that you can have more and more examples. Okay. Next, we have. Okay, so let's try again. Another example, a chemical engineer wishes to observe the effects of temperature, pressure, and catalyst concentration on the yield resulting from a certain reaction. So you have 3 items here. You have the temperature, okay, you have pressure, and a catalyst. Okay. If she intends to include 3 different temperatures, so what that might be, temperature 1, temperature 2, temperature 3. So you have 3 ways to do the temperature. 9 pressures or 9 different pressures. Okay, and 2 levels of catalyst. So you have 2. Okay, so your N1, how many is your N1? Your N1 is equals to what? Your N1, I don't have a pen here. N1 is equals to 3. Because you have 3 different temperatures. And N2 is you have what? How many? You have 9 different pressures. Okay. Later on, I'll put my... During our calculation, I'll be using my um, notebook for this so that we can uh, neatly use it. Okay, and then your N3 is equals to what? 2. So you have what? Based on our formula earlier, we have N1 times N2 times N3. So how many times, or what will be our, how many different runs must she make in order to observe each temperature, pressure, and catalyst combination? So the number of runs is equals to, okay, the number of runs is equals to 3 times 9, oops, sorry, times 9 times 2. I'm using my mouse, so please bear with me. Later on in our calculation, I'll be using my tablet for writing. Okay, so we have 3 times 9 is 9, 18, 27. 27 is what? 54. So you have, oops, shucks. You have 54 numbers. So let's see. This is correct. Okay, so let's see. Okay, so you have possible number of temperature. There you go. Okay, let's erase all. Okay, and then 3 times 2 times 9. You have 54 runs. Alright? So, this example will be very helpful for you to be able to count how many possibilities, okay, are there if there will be several types of tasks that will be happening. Later on, okay, I will be doing another video for example calculations. Okay? So, okay, how about next one? Okay, for the addition rule, okay, this time, so last time, previously we have multiplication rule. This time is addition rule. Okay, so it's quite different because in the multiplication rule, there are certain combinations that we need to do. This one, also there is a certain combination. However, for this particular example, okay, you're just going to see, okay, how many, okay, you're asked to pick a card from a standard bicycle deck. So you know that cards naman, no? Okay, so it's good if you have some playing cards there, okay, so that you can visualize. Okay, this deck contains 52 cards. So we have what are those cards? So we have the 4 suits, right? Diamond, hearts, spades, and clubs, each of which are numbered from ace 1 2 3 4 5 6 7 8 9 10, and then the jack, the queen, and the king, or the royal suits. Okay? In how, or the royal faces, sorry. In how many ways can you get a king or a black card? Okay, so can you think about this one first? So how many ways can you get a king or a black card? Okay, in how many ways can you get a king or a black card? So to get a king, you need to have what? 4 of those, diba? Out of the 54 of out of the 52 cards that you have 4 kings there, diba? For each suit, correct? Okay. Now, how many black cards are there? Okay, so you have 13 and then 13. So you have 26 black cards. However, okay, okay, you have 4 kings. However, within those black cards as well, out of all, one of the, on those 26 cards, there are also 2 black kings included in that 26 cards, right? So we're trying to prevent double counting. Okay, so it means that we're gonna be recounting the king again, or 2 of those kings again twice. No, so we need to subtract those 2 black suit kings. Okay, so that we consider only the 4 kings and then the rest of the black cards. Okay. So hope this is quite clear because we have two black suit kings there. Okay. So how many are there? We have 28 ways to draw a king or a black card from the deck. Alright? So in the multiplication rule, we have n1 times n2 times n3, n4, n5, okay, ways to do that. In addition rule, okay, in the addition rule, we have the m number of ways plus the n number of ways, okay, and then minus what can be accomplished in each of it, okay, or the mutually inclusive one, okay. So we removed in this example, okay, we remove in this example the black suit king because within the four kings, there's already those two black suit kings. Okay, so we put it here only. Now, we added all of the all of the 26 black cards, including what? The two other kings. So if we're just gonna be straightforwardly adding them together, no, there will be double counting of the black suit king. So you need to remove one of it so that it should not be double counted, right? So make sense? So if k is equals to 0, the task can be A and B are said to be mutually exclusive. So later on, we will be putting another example for this addition rule. So I actually prepared several examples for each, no, so that you can be guided accordingly. Okay. So you need to prepare for this because there's a lot of tricky questions on this one. Okay. So how many? Let's have another example. Okay, so how many positive integers between 5 and 31 are divisible by either 3 or 4? Okay, so for those that are divisible by 3, we have 9 integers. For all that are divisible by 4, we have 6 integers. And subtract it from the number of integers that are both divisible by 3 and 4. Okay? Because that will be double counting again. Okay? Does it make sense? Okay. How many positive integers between 5 and 31 are divisible by 3 and 4? So later we'll be doing a visual counting of this. Alright, so for now this will be more of the explanation on how the formula works. Okay, so there are how many? There are 13 integers divisible by 3 or 4. Alright, so that will be 9 plus 6 minus 2. Okay, so that will be 13. Okay, so let's have hope for this. Okay. So a developer, let's try to answer this one later, but I'm gonna be reading it through you. Okay, a developer of a new subdivision offers prospective home buyers a choice of two-door, rustic, colonial, and traditional exterior styling in ranch, two-story, and split-level floor plans. In how many different ways can a buyer order one of these homes? So this one is an example of what? A multiplication problem or a multiplication rule counting. Alright? So I leave it to you for now, but I'm gonna be having a solution in another video for this. Alright? Next is Sam is going to assemble a computer by himself. Okay, those who are like to do computer assembly. Okay, he has the choice of ordering chips from two brands. So maybe that's Intel and AMD. Usually those are just the two contenders. Okay, a hard drive from 4, memory from 3, and an accessory bundle from 5 local stores. How many different ways can Sam order the parts? Alright, so copy this question. I think this is already in your PowerPoint. No? So, try to ano na lang later. Try to answer. I'll give you time. And then, I'll be giving another solution for this one. Alright? I'll be answering that. Okay, next is you have 5 chips numbered 1 to 5 or are in a container. You are asked to get 3 chips from the container. I'll be putting this on a discussion so that you can um, put your answers there. Okay, in how many ways can this experiment be performed or how many possible outcomes are there if sampling is done without replacement? Okay, and then with replacement. Okay, consider the same problem as in one above. Okay, but this time you are going to get only one chip from the container. If the number of the chip is even, you have to roll a die. On the other hand, if the number of chip is odd, you have to toss a coin. Okay, so this is more convoluted. So this is a fun to answer. Okay, how many possible outcomes are there in this experiment? All right, and then another is you have how many even four-digit numbers can be formed from digits 1, 2, 5, 6, and 9 if each can be only used once. Okay, this one is a trick question, ha. Um, just remember that there should be four-digit numbers. Okay, so next, three boys and three girls are sit in a chair arranged in a straight line. Okay, how many seating arrangements are possible if are these all exercises now for the counting techniques? I think this is all. Let's check. Oh yeah, I think this is all. Okay, three boys, three girls. Okay, so write it down there. Okay, next is we have how many three-digit numbers can be formed without repetition across all of the numbers? 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so I'll be putting this up, okay, on your discussion so that we can answer them, no? So that you can provide your solution there. All right, so that will serve as your attendance for today. For the permutation, I'll be putting it up Tuesday, okay, for the permutation, for the continuation of our discussion for this one. But for now, concentrate on the counting techniques. All right, so if you have questions, kindly message me directly. Okay, if you have other questions, but I'll be putting up more examples in a while. All right, for the counting techniques. So again, I'll be seeing you in our next session. Okay, so I'll be putting this up in an announcement. All right, so bye bye.